We have 2 more talks on the schedule. And Pavlos is already preparing down here with a bottle of beer, so it's going to be probably very amusing. The next talk, he's going to talk about AWS, Python, and FinTech. And I think, Pavlos, you need to start moving to your notebook, and there's the mic there. So please take a seat, and then we will continue. By the way, I wanted to mention, if you want to get in contact with us, and you're, let's say, too intimidated to talk to us, which is perfectly fine, of course, we have a box there which says, contact me, please. You can throw your contact details in there and maybe describe yourself a bit, and then we get in contact with you, and maybe we can have some discussion offline. Thank you.
We have some fantastic names for beers. And we have more pizza later on as well, because I think we ran out. So, no technical stuff from me. Does anybody recognize this? Any radio amateurs here? But today I'll tell you a story. So this is the beginning. That's early 80s. There was no internet that we know of. I know you're all used to phones, high bandwidth, but this is what we had then. This is a ham radio operating in about 10 megahertz to 30 megahertz. And it was incredible. I went to a high school that had a radio club, and this is the antennas, and you will turn the antenna, and like you do today with Twitter, that you had a channel, and you just type something, and people who subscribe to the channel can see it. You will go to some frequency and call, and every ham radio, every operator has a call sign, and people will respond. And we didn't have... especially I'm from a small island, we didn't have exposure to the world, so suddenly you will call your call sign, your name, essentially, and people from all over the world will reply, and you have a conversation. So it was amazing, it was eye-opening. Wow, we can actually talk with the world, not just through TV, see things. It was quite an amazing experience, but it became really interesting when the computers came along. So this is a ZX Spectrum. That was my first computer. It had 48, I got the big one with the big memory, which was 48 kilobytes. That's the kind of memory we had. And it didn't take long to realize that you could put the two together. So instead of sending voice, you could send beeps that represented 1 and 0s, which initially didn't look too interesting, but then suddenly we got the realization that if we could just send the 1s and 0s, then it didn't matter what it was. All we needed to do was to digitize something so we could send anything. So protocols started developing, like now we have TCP/IP. We're talking about very primitive protocols of how to encode things and send them across that all over the world. What is actually just a parenthesis here. We didn't have the problem with TCP that you had to send to everybody and make a connection to everybody and essentially duplicate the bandwidth. We just send it to everybody. It's a radio. You're broadcasting. So when we managed to do that, there was all these protocols being developed, one of them called RTTY, that you were able to send characters. So suddenly you will connect this with this, and you will type, and they will appear on the other screen. And of course, then immediately you could see that, all right, if we can send characters, we can encode an image as an ASCII art and send that too. So people started sending pictures. That's early 80s now. And of course, interestingly, the first pictures that people started sending were cats. We're still sending cats today, just bigger volumes. Billions of cats are being exchanged on YouTube. This is how it looked. So, well, I couldn't find a cat, but that's how it came out, because we didn't have well, there were screens, but that's how it all started. I'm old. Point is here that nobody could see at the time what it meant to bring together telecommunications and digitization. You put the two together, the whole field is still playing out. We couldn't see then what it meant to have these two together. It meant Facebook, it meant YouTube, it meant communication across the board, it meant phones, it meant everything. We couldn't see these things. But they're all made possible. It's still playing out. So sometimes when two technologies come together, two possibilities, they open up the solution space to such a degree that initially just we don't even have the imagination of what they can be used. And I think right now we're seeing another transformation. That's what I will be talking about. But then 20 years later, that brings us in the 2000, I would say, my friend that we were doing this, sending cats to each other with Russian radio amateurs and Belarusian radio amateurs, because we're a small island, everybody wanted to talk to us so they can get our card from Cyprus. So the co-founder of Point9 was working as head of credit derivatives in a big organization, and I was working in the US processing climate data for climate research. And we were both facing the same problems. So we get together, have a beer, and we both had the same problems. How we were getting all this data coming from satellites at a time that we didn't have all this processing power, we didn't have Amazon, and we needed tools to make sense of this data. We needed the ability to answer questions quickly. We couldn't really write everything in Fortran. We're writing Fortran. The climate models are still in Fortran, I think. They were when I left. They were trying to convert them to C++. They were failing all the time, so they were keeping them in Fortran. And, but we needed a way to get to the data quickly and answer questions. They were looking how to solve this problem, and then we came across Python. I came across Python because someone told me to check out Perl, and I went to the library, and it was Perl, and it was alphabetic, and then it was Python. I checked Perl, it looked like nonsense. I opened Python, it looked like something I could read, so I chose Python. But what it also gave us is that very early on, one of the senior Python developers created these numeric extensions, which was a matrix component. It was a C-based, it was called numeric extensions, numlib, now it's called numpy. It went through different names, which you were able to load data very compactly and run linear algebra operations very quickly on it. And basically, they were fast, so we could, and they made good integration with various libraries, scientific libraries, so we could load all this data quickly. And it didn't matter that they were Python, they were very compact. We weren't loading them into Python lists. We're loading them into this low-level C structure, which is still being used. And on top of that, it gave us, it's a very expressive language, Python. So we're already dealing with problems that were quite hard. Were quite hard to reason about in terms of science. We didn't want to deal with all the other computer science or language science constructs on top. They were quite hard to deal with anyway. So we wanted something quick and easy to deal with. So for example, the expression on top is, well, if you don't know Python, it reads like what a normal human being will tell another normal human being. Trade for trading trades, if it's valid. It sounds something that is reasonable. Also, we were able to write things like this. B equals A times 3. Very simple expression. If A is 5, B is 15. After a beer, maybe I don't even get that correct. But what's really important is that in Python, you could put A there. It could be a tensor, that's what we're using. And the expression remains the same. So we could type, we put in A tensor, and it could be a tensor of floats. It could be a tensor of integers. It could be a tensor of anything. And it will work. And it will take every single number in the matrix or the tensor and multiply by 3 and give you B. And that's nice. You cannot do it. Try to do this in Golang or any of these fancy new languages. You cannot really do it as expressive as this. You have to iterate. You don't have generics. Problems. Another thing is that you didn't really need a DSL. Even for a relatively complex, well, not complex here, but even a simple linear algebra expression, the transpose of two matrices equals to the multiplication of the transpose of each matrix, it's readable in Python. This is a valid Python expression. I don't need to design a DSL for it. So I think all of these things together is the reasons also that now Python is such a prominent language in the data field. The numerical expressions, expressivity. If you're working with big data these days, you cannot really avoid Python. The other thing that it gave us was generality. We didn't need two languages anymore. We could program the connection to the API and a connection to a database and get everything together and parse it and use the numerical expressions and get the answer. So we found ourselves putting more and more and more things into Python. Initially, we thought, no, this thing is not going to scale. Let's write it in Fortran. Let's write it in C. No, it scaled. It worked. So then we got bigger machines, and we put even more things in Python. And now we're only writing Python. Well, sometimes maybe a little bit of C. But also at the time, Python gave us an ecosystem. So we needed to parse data. We needed to parse data at scale. We found this library called mxparser, which was written in C. It was extremely fast. The API of the library was very well designed. So we started using it to parse all kinds of data thrown to us by clients. And then when we needed more support, we contacted the author. And that was a nice thing about Python. You could find the right people. So we contacted Marc André, who is the chairman of EuroPython now, said, OK, can you help us? And he said, yes. And I think he regretted it now, because it's been 15 years now that he's helping us. So that was also another important thing that Python gave us. So we formed Point 9, basically, to take advantage of this. Initially, we focused more on the front office. We were writing the quantitative libraries, how to do the risk for a credit default swap or a CDO. Market collapsed. In any case, we found out that the biggest problem that the clients were facing, big banks, hedge funds, asset managers, was actually on the operational side, how to get data from one place to the other, which is what we were doing at scale in university. Problem looked simple, problem looked boring, but actually when we started working with it, it was very interesting because there was all these things that we need to get right, how to store data, audit trails. We get to learn about event sourcing, that is now a popular way of building applications. We got to know about how to scale things horizontally, how to break this into workflows, concurrent processes, data flow models. And what we're doing really, trade processing, is essentially a data processing and a management problem and a quality control, because you always get exceptions, you always get bad data thrown at you. And you need to manage that in a way to reduce exceptions, because one of the big costs of these organizations is having people there looking at errors and fixing them manually. So the clever thing is, how can you take errors and figure out how to handle them in the most efficient way? And again, you need very agile tools. A typical workflow, I'm not going to dwell on this because Evgeny mentioned it before. We take data, connect to multiple sources, dealing with various formats, parse them, make RPC calls, access databases, then lots of calculations, and then we disseminate the data to third parties. This is how it looks, typical workflow. I don't intend to go over this. Not even if I didn't have any beers, or I didn't have any beers. It's just to show you the complexity we're facing. So we don't want too difficult tools. You have prime brokers, fund administrators, custodians, bank accounts, payment systems, SWIFT, all kind of stuff, legacy stuff that you need to connect, make sure things are going, and through all of these things successfully. If not, what do you do? Good question. What's the impact on our business, though, in terms of Python? So Python uniquely allowed us to focus a lot more of our resources into solving client problems. That's really the gist of the story. That's what we see Python really good at. It lets you focus on solving the core problem instead of worrying which source control system to use, what merging method to use, which packaging system to use, all the other stuff. And I think it's still the case, although most languages now, Java, you have Kotlin, you have Go, you have good ecosystems, is much better now than it used to then. I think still Python has the edge here. Python was not enough. Okay, we can write the code, we can solve the problem, but where do we run it? We can't run it on our laptops. We're a small company, and certainly we cannot go and buy 2,000 servers from Dell, set it up in a warehouse or something, and run them, because once a month we need all this processing power. So then Amazon came and gave us basically what Amazon did. In short, effectively, what they did was to turn an infrastructure problem, a physical problem, into a programmable API. And this gets me to the first slide. What we're seeing here is a transformation of physical processes into APIs, into programmable APIs. And one of the effects that we are seeing is this great increase on the solution space. So before you could just put a server, now this is how we set up a server. This is actually valid Python code that when we run it, it creates an M3 2x large instance, it's a type of server on Amazon, in US East Coast, and we can replace that with Tokyo, Ireland, Frankfurt, South Africa, whatever we want. We also can put it in a loop and fire about 1,000 of these, solve the problem, switch them off. So this is what we see as transforming, in that the cloud has transformed infrastructure provision into a coding exercise. This is a big deal, and it's just the beginning. We're going to see a lot more of this. And when you get this programmability of infrastructure and the coding ability together, we're going to see solutions that were not even imaginable before. And we're just in the fintech space, but I think we're going to see a lot more of this, not just Amazon Cloud. Inexpensive storage was also very important for us because it lets us address one of the biggest problems we are facing in a unique way. So one of the biggest problems our clients are facing is uncertainty. We do not know now what the regulators will want in 6 months. We do not know now what the market will be in 6 months. So how are you going to architect a warehouse, let's say, if you cannot even today ask the questions you want your warehouse to give you? So we tried various iterations that they don't work. At least we couldn't make them work. So we still had to do something about it. So we said, okay, let's take all the source data, just put it on S3, because it's so cheap, it doesn't matter, it doesn't cost us anything. So we'll go to the client and say, okay, they will tell us which fields do you want from our system. And then usually that's how it happens. You allocate project management resources, and you sit there and you spend months thinking what the problem is, and then analyzing it and figuring out what the data is that you need, the precise data, and then there's a project, and it starts and gets developed, and 6 months later it's done. So we said, we don't care. Just give us everything. So what do you mean everything? You don't even know what they are. We don't care. Just give us everything. 400 fields. Yeah, just dump it on us. Presumably, we thought, if we get all the raw data, and we put a process to get all the raw data, then it's just how they're there, so it's a matter when we need them, we can run queries on them and find out what we need. So at least we have the data. And this only became possible because storage was cheap. Otherwise, we couldn't deal with all this data in expensive storages. And of course, if you have data in a nice, well-designed database, you can run quickly queries, you can index. But if you have just a lake of data, it gets harder. So how do you do it? Again, Amazon here can help us because you can fire a lot of processes, run queries, shut them down if you want. And now we're also experimenting with Lambda. Basically, that doesn't even include servers. So you just write Python code, you put it on to Amazon, it gets some input, does something, finishes. You don't even know where it ran, or what server, or operating system, or stacks, or network problems, nothing. So, okay, we built the company we had 20 people, so we do all these things with 20 people because of Python and AWS. And last year, and why we're traveling a lot now, is the biggest Japanese bank approached us and said, okay, you solve this problem, you're dealing all these things, you're just 20 people, how do you do it? And we said, it's Python and AWS. I said, well, we have Python, we have AWS, and we cannot do it. Well, then it's us. So they said, okay, so come in, solve our problems. So suddenly they dumped on us their problems. That this is a 1.2 trillion in assets bank. All over the place, they have 100,000 people. So now we're facing much bigger scale. Many more businesses to understand and make sense of. Bigger scope. So we have they have many systems. We have data cleansing, deduplication at scale, consolidation, normalization. Can we apply machine learning here? Machine learning is good for classification, finding patterns. We have user interface challenges, lots of them. How do you do this exception management? How do you compose? Not just, everybody talks about composability. We usually mean as programmers, composability at the code level. You have a function, you have another function. Here we're facing composability at the operational level. How can we compose a manual process that will remain manual because there's a spreadsheet that uses a library that's only available in the spreadsheet, so the data have to go into the spreadsheet and then get out on the out. And how can you build a system where possibly you can break the system, the process into half, and then put another step in there that's manual. So you need to compose at the operational level, and that's hard. We don't know how to do it very well yet. We have process challenges, and I will stop here with what I think the only message I have to say tonight is that transforming rigid physical processes into programmable systems and APIs is really an extraordinary development. We're not even aware of the repercussions yet, and the cloud is just the beginning. So thank you all for coming. I think there's a lot more beers that we have to drink, they told us, before we leave, so enjoy the party. That was it. There's another talk from my colleague Dimitri. And then it's beer time again, and pizza time, I believe.
Thank you very much, Pavlos. Any questions?
Yes, questions. No questions.
Who thinks this is exciting? Come on, I mean.
Thank you for your talk.
Okay.
Just one question. Have you experienced some performance issues because of you use Python? And as I understood from your talk, you use Python for significant calculations. And did you have some performance issues? Because as I know, Python is not so fast language because it's an interpreter.
Well, yes, I mean, Python is slow in some measures, but if, let's say, you run a process and you profile it, and that's something very important before you jump into, before at least we jump into making any assumptions of what to do, we profile. If you profile and you find out that a process takes, let's say, 1 hour, and 59 minutes was I/O, and 1 minute was Python, even if I make that minute 0 by using, I don't know, assembly, I'm going to go to 59, so I might as well spend my effort on the I/O side of things. So we are very much I/O bound. And actually, Amazon is not so good on the I/O. The I/O is the weakness of AWS. It's a bit expensive, we find. So we're always I/O bound. So Python doesn't really matter much.
Okay, so just to summarize, one of the reasons why you used Python because of it has powerful DSL for mathematical calculations, right?
That's right, yes.
Okay, thank you.
Actually, at that level, once you have things into the numerical expressions and you run calculations, it's quite fast there, comparable with anything out there.
I think what you sometimes hear that Python is slow. I think this is you have to look more at the context of what you're talking about. So, for example, if you look at NumPy is really fast, and what's very nice about Python is that it gives you access to this performance in a very easy and very understandable way, which is why the data scientists, for example, are picking up Python as their standard language. I mean, if you go to data scientists now, they have two languages they use. One is R, which is a statistics language, and the other one is Python. And why is this? Because all the libraries that you have in machine learning and data analysis nowadays have Python libraries available, and it's very accessible for them. Let's say 10 years ago, the situation was similar for, like, say, for chemists or physicists who did not necessarily know programming. So they went to NumPy to fix their problems, and it was very accessible for them. They did not have to go to C anymore to fix their problems. And I think that's the main advantage of Python. It's not so much that Python itself needs to be fast, it just provides the interfaces to fast libraries. Yeah? So I think that's the main advantage of Python, making things accessible.